Okay, so we are in Statistical Rethinking, second edition, chapter 13, and we're on the last medium difficult question, question 13M6. Okay, here's the question, and basically what we're going to do is we're going to have a single data point at y equals 0, and then we are going to model, or we're going to use different models and then compare the prior distribution with the posterior distribution and the likelihood. So I'm sorry if that doesn't make sense, but you'll see here in a minute. But we have 4 different models. One where the data and the mean of the data are distributed normally. One where the data is distributed as a student distribution, student t distribution, and the normal is still distributed normally. One where that's reversed, so now the data is distributed normally, but the mean is distributed with a student distribution, and then where both are distributed with student distributions, student t distributions. Okay. So the first part is I'm just going to create these different models here. Okay. So hopefully by now you're pretty good at putting something like this into a model. Okay. So this is what it looks like. Okay. So you can look at the data, or look at the models or the code for yourself. And I've already ran this. And the next thing that we're supposed to do, according to the question, is to estimate the posteriors for each of these models, and compare the results. Okay, using the properties of the distributions. Okay. So let's go down here. Okay, so for each model, I'm just going to take the posterior distribution and then plot mu here, right, which is the parameter that we're estimating. Okay, and then along with that, I will plot the likelihood as well as the prior. Okay, the prior for mu, right? So likelihood is the data given, given all the different parameter values, and then the prior is the possible parameter values for the parameter. Okay. So this is what we get. So here we have the normal model, and then the data is distributed as a t distribution, and the prior as a normal. Now in the bottom left, we have that the data is a normal distribution, and the prior is a t, and then we have both of them are t distributions. Okay, so you can kind of take a look here and see what's happening, but let's try to pull out some themes here as to what's happening. Okay, so so where I want to start with is with these two diagonals here, with the Tn and the Nt model. Okay, actually before I do that, just I mean, you can look at the code to see what's what, but the thin solid line is the likelihood, the dotted line is the prior, and then the thick solid line is the posterior distribution in each of these. Okay, and so now you see that with the Tn and the Nt, you see that the posterior hovers either over the prior in the case of the Tn model, or the likelihood in the case of the Nt model. Okay, so what's happening here? All right, in the Tn model here, again, the likelihood is a t distribution, so this curve right here is representing the t distribution likelihood, and the prior is a normal distribution, which, I mean, you almost can't see because it's covered by the posterior. Okay, so what's happening here? Well, notice that the normal distribution, which in this case is the prior, is less permissive, or it's more restrictive over, over possible values, right? I mean, that is the difference between a t distribution and a normal distribution, is that the t distribution spreads its probability mass over a wider area, right? And so what we have then is that the t distribution, even though it's a little bit hard to tell on this picture, has quite a bit of probability mass over in the same domain as the normal distribution. And the normal distribution is very stingy with the values that it permits. And so what ends up happening then is that you observe your data. Here we just have a single data point, right? But you observe your data, And because the t-distribution permits data to be way out on its tails, it's fat-tailed, the compromise that is struck between the prior between the data, the likelihood, and the prior is that most of that probability mass stays on the prior, right? It doesn't shift towards the likelihood. Why? Again, because the likelihood is very broad, right? It gives sufficient probability mass to the domain of the normal distribution, the prior distribution, such that the prior distribution sucks up, all of the posterior mass. Now, conversely, now we have the roles reversed here in the bottom left, where the prior distribution is the more permissive t-distribution, and the likelihood is the more restrictive normal distribution. And so now we see the exact opposite thing for the inverse reason. Okay, the permissive prior t-distribution says that values way out on its tail here are, still have sufficient probability mass such that when we observe something out here, that the posterior is allowed to shift all the way, basically all the way over to the likelihood. All right, so that's what's happening there. So now what happens if the prior and the likelihood are similarly stingy? Okay, well then you get a compromise in either the normal or TT distribution. Okay, but these look very different. So what's happening here in the TT distribution, right? So we have two equally stingy, or I guess non-stingy distributions that at their tails there is sufficient probability mass at their tails such that it's overlapping with the bulk of the other distribution. I hope that makes sense, right? And so what ends up happening is they end up sharing all of the posterior mass between the likelihood and the posterior. Okay. Now, conversely, when you have two normal distributions that have very restrictive tails, right, where there's not a lot of overlapping area, the compromise that you get now is this kind of dead center normal distribution that that puts all of its posterior mass in between the likelihood and the prior. So I hope that you can kind of imagine how this is happening when you have these two competing forces, and two normal distributions are very, call it, standoffish to one another, right? And so and both equally strong. And so what happens is they end up splitting the posterior mass between them. But when you have two, and we'll call the two t distributions cooperative, right? They overlap domains, right? Such that, so they overlap domains such that they end up sharing the probability mass. Okay, so that's a little fable, I guess, but maybe that helps make it clear. But anyway, so I guess probably some greater themes here is that, and we should already know this, but when we have more permissive prior distributions, we will tend to give more weight to the data, to the likelihood, right? The posterior will shift more towards the likelihood, more towards the data, right? Conversely, if we have more restrictive priors on our model, then the data will not have as much of an impact. Now, if we were to have a lot of data here, right? This is just one data point. So let's take this TN model where all the probability mass stays over the prior. Well, if we had lots and lots of data, then the posterior would eventually be overwhelmed by how much data you had, and the posterior would shift towards likelihood. But okay. Anyway, I think I've said enough here.